Here's another circuit with the diode in it that we're going to determine the state of the diode, and then once we have the state of the diode, we'll determine what the current for the diode is. And we're treating the diode as ideal, so we're going to use the ideal diode model as we did before to find state. Okay, so again, the state is whether it's forward bias or reverse bias. So here I've taken the circuit, redrawn it with everything the same except we replace the diode symbol with an open. Remember, the arrow side is the anode, the line side is the cathode. So now VD, as before in the model, it's defined as VA minus VK. So now we just got to find the voltage on each side of the open and take the difference, and that's our diode voltage. So first we'll start here, okay, and notice the bottom node here is ground, okay, as it is in the top picture. So VK, that's the voltage at this node with respect to ground. Well, there's a 5 volt source and a 1K resistor connected between ground and node K. And as you learned in your circuit theory, anytime you have a source between a node and ground, that node is just equal to the source value. So you see there's 5 volts right at this node, and then between this node where there's 5 volts and VK, the node that we want to find the value of, well, we got this 1K ohm resistor. That 1K ohm resistor has no current because of this open, so the voltage across it is 0, and 0 volts across something like a resistor or a short, remember a short has 0 volts, well, that means the voltage is the same on both sides. So 5 volts at this node, 0 volts across the resistor means as we go from this node to this node, we don't change any voltage. So VK is also 5 volts. Alright, so now we just have to get VA. VA is the voltage at this node with respect to ground, and that's equal to the voltage across this 1K. And one way to get VA is just to use voltage divider, right? Because we have a series circuit here. Current is only flowing in this path since no current flows through the open. So anytime I have a series circuit, a single path for current to flow, I can find voltage across series resistors with voltage divider equation. Again, that's from your 201. So this is just going to be 20 times 1K over 2K, right? Because voltage divider, you put the resistor you want the voltage for, which is the 1K, in the numerator, and then the sum, the Req of the series resistors, goes in the denominator, which is 2K in this case, so 10 volts. You could also solve this problem by just setting up a node voltage equation here at node A. Alright, but either way, we come up with that the diode voltage is 5 volts. So conclusion, okay, the conclusion is that our reverse bias assumption was incorrect. This diode's really forward bias, right? Since the diode voltage is greater than 0. Alright, well now since we found the state of the diode being forward bias, let's find what the current is. Okay, let's find what that forward bias current is. So to find the forward bias current, okay, which is flowing anode to cathode, okay, this current right here, this is the circuit that we would need to analyze, okay, where now the diode has been replaced with a short. Again, we're treating the diode as ideal. So one way to solve for that current is to use node voltage method. I mean, you could also do mesh, right? You have two meshes here, so you could do mesh I1, mesh I2, write your KVL equations, and then whatever you get for I2, that would be the diode current, since I2 is the only current defined through the short that represents the forward bias diode. But I'm going to use node voltage method. So this bottom node is our ground. This node over here is known, 20 volts. This node here is known, 5 volts. So we're just left with this one node, okay, that I'll call VAK. Okay, remember, when there's a short, it makes it all the same node. When there was an open here, you know, we had a node on each side of the open. But once you put a short, this all becomes the same node. So I'm going to define my currents to write a node voltage expression. So I'll say this is I1. Okay, I'll say this current here is I2. And then I'll say this current over here through this 1K is I3. Alright, and remember, wherever current enters a resistor, that's the higher voltage end. So now doing node voltage method, I'll do KCL at node AK. So we got I1 flowing in, and that's going to equal I2 plus I3. I1 is 20 minus VAK over 1K. I2 is VAK minus 0 over 1K. And then I3 is VAK minus 5 over 1K. Alright, so one equation, one unknown. If you go ahead and solve for VAK, you should get that VAK is 25 thirds. Okay, 25 third volts. So the current ID, okay, the forward bias current through the diode, is just going to be the same current as through this 1K right here, since the short in this 1K are in series. Okay, that equals the 1K current. So that's this term right here, okay, I3. So 25 thirds is 8 1/3. So 8 1/3 minus 5 over 1K. We have a current of 3 1/3 milliamps. That's the ideal forward bias current. Alright, so that completes that problem. We got one other problem for this video, and here's a problem that has two diodes in it. So we'll see how to handle this, and really when you have more than one diode, it's the same approach. It's just you always want to start with a reverse bias assumption, again using the ideal diode model. So we're using the IDM again. So we start with a reverse bias assumption. So these two diodes are replaced with opens. This is D1, this is D2. Okay, and now it just becomes a nodal analysis. So we'll start here. Well, notice that the bottom node is ground. Okay, so now we'll start right here at this node, okay, which is VK of D1. Well, you know when there's a source between a node and ground, that node is just equal to the source value. So VK for D1 is just 12 volts. Okay, then we come over here. Let's do this node next. The voltage at this node with respect to ground is just the voltage across the 20K, and there's no current flowing through the 20K because of this open. So there's 0 volts across the 20K. So VA for D2 is just 0. Okay, 0 volts. So that leaves this node, which is both VA for D1 and VK for D2, right? Same connection point. And here is a known node of 10 volts. And there's 0 volts across this 10K ohm resistor because there's no current flowing through it, right? I is 0 here. There's no complete path for current to flow through that resistor back to the sources. So 0 volts across something means voltage the same on both sides. So 10 volts on this side with respect to ground. 0 volts across the 10K means there's 10 volts at this node with respect to ground. So 10 volts for VA for D1 and 10 volts for VK for D2. VD is just VA minus VK, so minus 2 volts and minus 10 volts. So the conclusion is that here, both these diodes, the reverse bias assumption was correct. Both these diodes are reverse bias, and therefore ideally their currents are 0, right? Because remember, reverse bias, the diode doesn't allow current to flow. Alright, next video we'll look at some common applications of diodes.